Pick up a paperclip. Hold it flat on your palm. Now bring one of those cheap pizza shop magnets near it, the kind that costs less than a coin. Watch the paperclip jump off your skin and snap to the magnet. That moment, that quiet, embarrassing defeat of a planet weighing 6 billion trillion tons, is gravity's entire professional resume. Gravity just lost a tug-of-war to a fridge magnet, and gravity was using the whole planet. This is the weakest force in the universe, 10 to the 40th times weaker than electromagnetism, a 1 followed by 40 zeros. To count to that number out loud, second by second, you would need longer than the age of the universe. Then you would need to multiply by 1,000 and start over. That is how much weaker gravity is than every other force you interact with daily. And here is the part that should stop you cold. That weakness is not a defect. It is the only reason you exist, to laugh at it. Shift gravity by 1 part in that absurd number, 1 atom on a dial the size of the cosmos, and stars never form, atoms never bond, and you never show up to wonder why a magnet just beat the planet. Lucky us. In 1915, Einstein gave us the cleanest way to picture what gravity actually does. Imagine a bowling ball sitting in the middle of a stretched bedsheet. The sheet curves down under it. Roll a marble nearby, and the marble doesn't fly toward the ball. It follows the curve. That curve is gravity. Not a hand reaching out and grabbing. A bend in the fabric of space itself, carved by mass, followed by everything near it. The real universe isn't a bedsheet. The image breaks fast, but the picture buys you the only thing that matters here. Gravity does not pull. It shapes. It rearranges what straight even means. Now here is the part textbooks rush past. A star is not a ball of fire. A star is a negotiation. Gravity presses inward, trying to crush every gram of hydrogen into a single point. Nuclear fusion pushes outward, trying to blow the whole thing apart. Those two forces have to balance, not loosely, but with a precision that lets the negotiation run for 8 to 10 billion years without either side winning. 8 to 10 billion years. That is how long a star like our sun stays in business. Long enough for planets to cool, long enough for chemistry to get complicated, long enough for something on one of those planets to evolve eyes, hands, and a confused face, wondering how any of this got here. If gravity were even slightly stronger, that negotiation breaks. The star collapses in years, not billions of years. The factory closes before it ships its first atom heavier than helium. Slightly weaker, and the negotiation never starts. The hydrogen drifts apart. The star never ignites. The factory was never built. Gravity is not impressive because it crushes things. Any brute can crush. Gravity is impressive because it knows exactly when not to. And restraint, for a force, is much harder to explain than power. So let's quantify the restraint. Imagine a physical dial controlling gravity's strength. It runs from 0 to infinity. The zone where a universe can produce stars, elements, planets, and life is narrower than the width of a single atom on a dial, the size of the observable universe. A sphere 93 billion light-years across. That is the working range. 1 atom, on a dial 93 billion light-years wide. Push the dial slightly to the right, gravity stronger, and the universe collapses in on itself. Not in trillions of years, in minutes. The Big Bang becomes a big crunch before any structure can form. No stars, no galaxies, no second chance. Push slightly to the left, gravity weaker, and the opposite catastrophe. Hydrogen never clumps. The universe becomes a cold, thin fog of gas expanding forever, touching nothing, building nothing. The periodic table is a one-line document. Hydrogen, helium, end. Either side of the dial, you get a dead universe. The window where anything happens is impossibly narrow. Now here is where it gets uncomfortable. In 1979, the physicist Roger Penrose tried to calculate the probability that the initial conditions of our universe could occur by chance. He arrived at a number, 1 in 10, raised to the power of 10, raised to the power of 123. That number has more digits than there are atoms in the observable universe. Penrose wasn't writing a philosophy paper. He was doing arithmetic on what physics already accepts. We gave gravity a name, fundamental force. which is the scientific equivalent of calling someone influential right after they've lost a fistfight to a kitchen appliance. The label is generous, the numbers are not. This is the part the textbook handles by changing the subject. The standard line is that the value of gravity is what it is, and we should not ask why. But the value of gravity is the only reason anything in this sentence is happening. You cannot explain this precision by labeling it a coincidence. Coincidence does not arrive with this much specificity. To appreciate how far cosmic precision sits above human precision, look at what we built to measure it. In September 2015, a project called LIGO detected gravitational waves for the first time in history. Two black holes, each about 30 times the mass of our Sun, had spiraled into each other 1.3 billion light-years away. The collision released more energy in a fraction of a second than every star in the visible universe combined. By the time that energy reached Earth, after a 1.3 billion-year journey, it was a tremor, a faint shiver in the fabric of space. To catch it, LIGO had to detect a movement smaller than 1,000th the diameter of a single proton. To do this, humanity built two 4-kilometer tunnels in 2 American states, polished mirrors to nanometer precision, spent roughly 40 years and several $1 billion, and waited. Then it picked up the whisper. Meanwhile, a stray hydrogen atom in a dark nebula handles gravitational attraction perfectly. Every second, free of charge, no tunnels, no funding requests, no press release, it gets sharper. NASA launched Voyager 1 in 1977. Its trajectory through the outer planets relied on gravity assist calculations, accurate to 15 decimal places. Nearly 5 decades later, the math still holds. The probe is exactly where it should be, leaving the solar system on schedule. 15 decimal places. We can barely get 2 engineering teams to agree on inches versus centimeters. The universe handled 40. And on the bodies of the astronauts we send up, NASA's Human Research Program has tracked one consistent failure. In microgravity, human bone loses 1 to 2% of its density per month. Pull the dial down even a little, and the human body begins to dissolve. The gap between our highest engineering achievement and the everyday precision of cosmic infrastructure is not a gap. It is an insult. So consider what we are looking at. A force tuned so precisely that one atom of deviation on a dial 93 billion light-years wide ends everything. A negotiation between gravity and fusion that runs for billions of years on a setting we did not choose. Probabilities written with more digits than there are atoms to write them on. And a universe that arrived already configured, before there were rooms, locks, or any engineer to flip a switch. For something we keep calling random, it has a remarkably consistent signature, not power. Placement. You can call it luck. You can call it coincidence. You can call it the way things had to be because we are here to observe it. Each of those is a label, not an explanation. Improvisation, at this scale, has a great deal of explaining left to do. So the question stays on the table, exactly where the data left it. Who calibrated the weight of the universe this carefully, if no one ever touched the dial?